first of all, let me thank the organizers for organizing this wonderful conference. It's very nice to reconnect with I just wish our detectors are as sensitive as this thing. So we're looking at. So let me thank the organizers. It's really wonderful to, reconnect with old friends and collaborators, and also to get more acquainted with Rohini's friends and collaborators who are all here. So I'll talk a little bit about the work that I've done with Rohini. And so my physics journey with her, and I'll only really focus on one small aspect of it. Of course, Higgs characterization is a huge topic, and there are lots of things that have been done. This is not meant to be anything exhaustive, and so I apologize in advance if I've left out many, many things. So let me first show you this, which is a Diwali greeting that she sent me, and I'm sure she must have sent many people in the audience in 2022. So reminding me of her love for food and plants, but also, taunting us to come visit her in Bangalore. Okay, so only for your eyes, unless you are here in Bangalore. It's a little bittersweet for me because I couldn't make it, but now I'm here, and so I get to eat all the good food at the conference, but not with Rohini. So my physics journey with her started, of course, as a graduate student with her. And the first thing I actually did was, I have to remind myself about this, is to look at hadronic backgrounds at future colliders coming from Beam-Stralsund and Bremsstrahlung processes. And then, because the Higgs was discovered, we quickly shifted to Higgs. And so you heard a little bit about invisible Higgs yesterday. And then we did stuff about, anomalous Higgs in VBF. And then also, Devtosh mentioned charge and color breaking minima in the MSSM. But I will just focus on two things over here. One is CP violation, probes of CP violation in associated Higgs production at the LHC. And then also, CP violation in Higgs and top interactions, and I think Rahul spoke a little bit about this yesterday as well. So anomalous Higgs couplings, you will hear more. I think Professor Mulaitna might say more about this. I'll just be very brief. You can take the Higgs gauge boson, vector boson coupling, and in the standard model, you just have that piece over here. But then the most general Lorentz structure tells you that you could also have additional terms in the vertex. And of course, all of this can be generated through a standard model EFT, or it can be generated to some other more UV complete theory involving say fermion loops, for example. Okay. So just a quick notation. So I'm just reparametrizing everything a little bit over here. So I'm only focusing on this rescaling of the standard model coupling, and then the CP odd term, which has this Levi-Civita tensor over here. And the idea is that in the standard model, all of these additional pieces that I'm adding, these Wilson coefficients, are all 0. And so obviously the first thing to be very careful about when using something like this is unitarity. And so if you calculate our usual WW scattering, you will find that there are constraints on how much this Wilson coefficient, which I'm taking to be real for the time being, could be. And you can see that this is actually a pretty strong constraint. It should not be much larger than this. Ratio where root S is, of course, the center of mass energy over here. So please bear in mind that I will be that this constraint should always be there, but sometimes I'll be very lax about it. So let's first look at constraints on these form factors or Wilson coefficients. If you just, for example, look at Higgs rates, and so this is all very dated. So this is stuff that I'm not trying to show you the most up-to-date thing. I'm just trying to get to a physics point over here. So if you just look at, say, gluon fusion Higgs production at the LHC and try to fit these parameters to the observed values of these cross sections, you will end up with a plot like this. And so this shaded region, the blue shaded is all disallowed by this cross section, and then this shaded region is allowed. So you can see large regions of parameter space allowed just by looking at this particular cross section. And then, if you like, you can also look at CP properties, which I'm guessing you probably hear more about. Yes, we'll probably hear more about in the Higgs-Golden channel. And so if you put that constraint also on this plot, that rules out all of this portion, and so you're left with that. And so what happens when you now start looking at associated production? So when I started looking into this stuff in 2011 or so, the people were not taking this very seriously. Associated production, of course, got a big boost through looking at boosted B quark channels of the vector boson, and so this becomes a very interesting channel to also look at the LHC. And interestingly, what happens is when you have these additional Wilson coefficients and form factors, it affects the, for example, the transverse momentum distribution. It's obvious because now you have additional momentum factors in this vertex. And what that means is that this strongly affects the cross-section as well. So now, if in my fit, I also consider the constraint coming from VH production, then you see that there's this green region rules out a large part of it, and so there's a much smaller region only now that's allowed. And so this is entirely just by looking at cross-sections, okay? So, but of course, you can do a better job by looking at differential cross-section, and so the idea is to, for us, was to construct observables that one can look at that are sensitive to the CP odd piece in the matrix elements. So that really is looking at the matrix element squared and looking at the interference term between the CP even and CP odd parts. But this is a little tricky to do for this process at the at PP colliders, because at an E plus E minus collider, it's a CP eigenstate, right? So you know the direction of E plus and then you know the direction of E minus. Over here, also I'm being very loose, lax over here and saying that this is also a sort of CP eigenstate if you can understand which direction the anti-quark is coming from. And so that's hard to do at the LHC, but what we did was use the idea that parton distribution functions for valence quarks peak at higher values, so they will tend to be harder, and so this thing tends to be boosted more along the beam axis in this direction, and so you can kind of identify, looking at the rapidity of the event, whether which direction this quark came from. So that's basically the idea by looking at the parton distribution functions, and then you can construct observables that are sensitive to the rapidity as well, and therefore then also sensitive to the CP odd piece in the matrix element square. So we tested out various observables based on this idea, and we constructed, various asymmetries as well, and then looked at what those asymmetries would look like at the LHC. Now, something that Rahul also mentioned yesterday is that these interactions with gauge bosons are loop suppressed. So, for example, if I were to take if I were to believe that the CP odd bit in the Higgs-ZZ interaction came through, in fact, this fermion loop over here, where now I have a top quark which has some CP odd piece over here. Then, if I looked at, in fact, now Atlas and CMS have done these measurements on the CP odd pieces in BBF production as well. And so if I just take that combined thing, I get an absurdly large number for this this coupling constant over here. And of course, unitarity is violated, so this is not numbers that you should believe at all. So the point I'm making here is this is all loop suppressed, and so it's not where we are likely to see CP violation in the Higgs sector. We're more likely to see CP violation in the Higgs sector in fermionic interactions, and so that's what we then decided to focus on. And so if I play the same game, looking at just rate information, what can I constrain about these CP even and CP odd couplings of the Higgs to the top quark? Then you can make a figure like this, which is what we did with Housie and company way back in 2015. Of course, these are the updates to this. So what you're seeing here is this is the AT and this is the BT axis, and so that's the standard model there, and this is the 1 sigma allowed region over here. And this is just looking at rate information, and then of course, if you look at differential cross sections, this will improve, and so that's the next thing we did. which was to try to look at differential cross-sections. But before that, here are updates from the ATLAS and CMS experiments. So they're looking at, again, just this kappa t and kappa t tilde, which is the same as the AT and BT I showed you before, and the constraints that you have on these couplings in these various channels, okay? Coming from the TT bar Higgs production. And then, of course, Rahul spoke a little bit about this, using machine learning to do all of this stuff. We looked at, of course, the polarization of the top quarks and various observables associated with that to try and understand how one can distinguish. And so the idea what you should take away from this plot is it's different. Okay, whatever this observable is related to the polarization of the top quark is sensitive to the AT, to this beyond standard model pieces. And then we try to play the same game, which is also construct something that is odd under CP. And again, the idea is to, those kind of observables will be sensitive at really small values of the CP mixing. Okay, so these observables are better off when you have large CP mixing, and then those observables are better when you have small CP mixing. And so we were able to construct such observables, and our focus, of course, is, what was known at the time was, you could just construct certain observables by looking in the center of mass frame, in the rest frame of the top, and then the anti-top, and so on and so forth. But our goal was to try and construct something that's easier to do at a collider, which didn't require information about the top momentum, because that's hard to reconstruct. And so to remove some of that uncertainty in all of the analysis. And so we were able to construct these lab frame observables that can be used without having to reconstruct the full picture in these analyses. And it is also, and the takeaway here is, here's the plot from the previous slide, and here's the plot with this new the CP observable added in, and so you can see that these are different, and there's a bit of an asymmetry over here. And of course, one next step is construct the asymmetry and look at what can be measured at the LHC. And so this is what that looks like. Okay. So let me now come to something that I kind of worked on a little more recently. I moved away from all of this Higgs physics for a while, and then came back to it a little bit a couple of years ago. And this is looking at the linear gluon polarization in Higgs production, Higgs plus jet production, as a way to also test this CP violating interactions of the Higgs and top quark. So I'm calling it gluon linear polarization because I'm borrowing this from the TMD community, where they look at linear polarization of the gluons and protons. But here, really, I'm just looking at the polarization of the gluon in the final state. So that's what this is. So here's my incoming state. Here's my final state. And what you can do is to calculate the impact that the linear polarization has on the gluon jet. And the way to do that is to look at the interference between helicity amplitudes of this process. And so what we're doing is actually just constructing the density matrix for this process, for the gluon, in this final state over here. And the point over here is that when you construct this density matrix, the interference terms will then give rise to CP odd pieces in it. And so we looked at then what the impact of this is on the jets that are produced for standard model and beyond standard model. And we constructed various observables as well. I won't go through all the details over here. The important point being we need to be able to construct a infrared safe jet observable that can then be sensitive to CP violation. So what is this observable? The idea is to look at the jet in the center of mass frame of the process, and then construct a reference frame where z hat is the direction of the gluon, and then construct a direction for x hat and y hat, again given by the plane constructed out of the gluon and Higgs. Okay, and then once you have this reference frame, you can look at the energy distribution of the jets, or really, okay. you can look at or what we really look at is the transverse momentum around the XY plane over here that we have constructed, and see whether that's sensitive to CP or not. Now, a very similar thing was done, and Shankho's probably in the audience here somewhere. I had done this for Higgs production, but over here with a Z boson and leptons, so that's easier to do. So let's look at then what impact this CP violation has on this jet observable. So the main point over here is that, again, from the density matrix, you can see the CP odd pieces affect what the azimuthal angle distribution of the energy or transfer momentum deposits of the jet are going to look like. And so the different pieces in this density matrix affect whether this is going to be look more like a cosine 2 phi, or where this is the azimuthal angle in that constructed frame, or a sine 2 phi piece, and this is the one that's actually sensitive to CP, or linearly sensitive to CP. And so, if you take your jet, analyze the events, and then look at the transverse momentum or energy distribution of these jets in some way, and one of the ways which we already showed you, then you can see that there's a CP odd, C2 is odd under CP, and so you have something over here that maybe looks like this if this is positive, and if you flip the sign, then you have a distribution that looks like that, right? So how can this be used, and how useful is this going to be? That's something we tried to estimate. So unfortunately, it's not going to be super useful at the LHC, but hopefully at the FCC it might be more useful. But the main point is that this is not currently being used at all as information in the analysis. And here, what we find is that if we do have the FCC and we only use this observable and nothing else, then our estimate is that you should probably restrict this to about this mixing angle between CP even and odd to about 8.6 degrees, right? So this is just to point out that this is a useful observable and should be used, but none of the analysis or event generators that people use or parton showers that people use have this information in there. And it's a little unfortunate that the only parton shower that we have that currently, well, there are two now, but at the time when I was doing this, Herwig was the only one that had this information about the spin of the gluon, or the density matrix of the gluon in its parton showers. But that doesn't work as well. It's not as well supported, so it doesn't, unfortunately, that doesn't work. The other parton shower that's still being constructed is PanScales, and that also has this information. I believe the other parton shower, Alric, might have this information, but it's not there as yet. Okay, so the main point is, when you do your simulation, please also include the spin information, and that's going to be and the density matrix in the showers, so that's going to be important for testing CP as well. Otherwise, you can if you run your machine learning models, this information is missing, and you will not pick up on this information in whatever machine learning model you use. Okay. All right, so that's pretty much what I wanted to say. And so let me just quickly tell you that, okay, I focused only on this one particular aspect of looking at CP observables at the LHC to probe the interactions of the Higgs. So it's not a in-depth analysis of what the field looks like now. But when I put this paper out on arXiv, Rohini sent me a message saying, sounds like a good paper, right? Good that you returned back to this, all right? Of course, even though it's been a while, I mean, she was my supervisor until 2014, the immediate feeling that I got was this, right? Anyone who's seen this movie, Dangal, it's, this person is showering praise, but in very small bits, and so I felt very happy about that, okay? So I was really happy that she was reading the paper and she enjoyed it. All right, thank you, everyone.